This is the screencast for section 5.3, example 1, the properties of definite integrals. So in this section, first of all, we're kind of building up momentum to section 5.4 and every section following. This section, you're going to learn properties of integrals. These are your first steps to doing antiderivatives algebraically, other than the few examples we did with the power rule, you know, adding 1 to the exponent and dividing by the new exponent back in chapter 4. So these guys, these are your big properties. You've got to have these down pat and be able to use them. So here are those properties. First of all, order of integration. If you are integrating from b to a, so your lower limit of integration and upper limit of integration, if they switch, now you're dealing with the opposite value. So in other words, you can integrate backwards from right to left, but then it would be the opposite of what the integral would be from left to right. The zero property, the antiderivative from anything to itself is zero. That is simply because if you integrate a rectangle of 0 width, it has 0 area. Constant multiple. If you have, remember, an integral is a sum. It's adding a whole bunch of different things. So if you have a constant in here, every single piece you add up is going to have that constant in it, which means you can factor that out. You can pull that outside of the integral. Just a constant, though. So you can only split up multiplication when it's a constant in an integral. You cannot split up the integral of f of x g of x dx will never equal the integral of f of x dx times the integral of g of x dx. That will never, ever, 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 ever happen. Not a property. Don't use it. And then it also implies that you can factor out a negative too, just because it's a -1. So if you had the integral of from a to b of negative f of x, that's the same thing as negative the integral from a to b, or positive the integral from b to a. Oh. All right, number 4, sum and difference. So you can split up sum and differences within integrals because you have an integral which is a sum of different things. So like we talked about in section 5.2, you can break up those shapes into different parts and add them together. That's okay. So you can break up addition and subtraction in an integral. Now, additivity is a teeny bit different. The integral from a to b of f of x dx plus the integral from b to c of f of x dx would be then the integral from a to c. So if you're going from, on the x-axis, a to b, and then b to c, why not just do a to c all through the whole thing and add that all up together as one big shape? So now let's put these properties into use with example 1, using the rules for definite integrals. All right, so we're given a few things. We don't know our function, but we know that the antiderivative from -1 to 1 of f of x dx equals 5. We have no idea if a portion of this is above the x-axis and a portion is below. If it's all above, we don't know. The antiderivative from 1 to 4 of f of x dx equals -2. So now we know that there's more area below the x-axis than there is above the x-axis between 1 and 4 because its integral is negative. And the antiderivative from -1 to 1 of h of x, a totally different function, dx, is 7. So find each of the following integrals if possible. Here's where our properties will come into play. Part A, the antiderivative from 4 to 1 of f of x dx. Well, from 4 to 1, I know the antiderivative from 1 to 4, but because of the property that lets me change the order of integration, I'm going to say that this is going to equal negative, or opposite, the integral from 1 to 4 of f of x dx, which means it's going to be negative -2, so that is positive 2. Part B, the integral from -1 to 4 of f of x dx. Well, let's see here. -1 to 4. I know -1 to 1, and I know 1 to 4. So what I'm going to do then is I'm going to take the integral from -1 to 1 of f of x dx, and that piece, and I'm going to add it to a new piece, the piece from 1 to 4, and I can do that because that is a property of integrals. I'm just adding these two shapes together, and that would be, let's see, 5 plus -2, so 3. Now part C, there is a, you may be able to see what is going to happen right away here, but I'm going to write out all my properties just to show you how to use them. I want the antiderivative or integral from -1 to 1 of 2 f of x plus 3 h of x dx. All right, so first things first, let's separate f and h into two different integrals. So I'm going to do the integral from -1 to 1 of 2 f of x dx, and I'm going to add that to the integral from -1 to 1 of 3 h of x dx. Okay. Now I can take the coefficients and factor those out, because remember, an integral means sum, and if 2 is going to be with each of these rectangles on the inside of the integral here, then I can factor out that 2. So I'm going to put 2 times the antiderivative of -1 to 1 of f of x dx plus, and I can do the same thing here, so 3 times the antiderivative from -1 to 1 of h of x dx. So now the integral from -1 to 1 of f of x dx is 5, so this is 2 times 5, plus 3 times the integral from -1 to 1 of h of x dx is 7, so now 10 plus 21 is 31. Part D, the antiderivative from 0 to 1 of f of x dx. Okay, well, I know -1 to 1, and I know 1 to 4, but 0 to 1, can I just cut that in half? No, because I don't know that this is symmetrical. What if there's here's -1 and 1, what if there's tons of area above the x-axis here and then just a little bit here? I can't cut it in half because that would not accurately represent the area between 0 and 1 of f of x dx. So D is actually not possible to determine. E, the antiderivative from -2 to 2 of h of x dx. Okay, well, I know the antiderivative from -1 to 1, so can I just multiply it by 2 since it seems to be going twice as far? Well, let's see. The antiderivative from -1 to 1 is 7, so there's like an area of 7 up here. Now I want the antiderivative from -2 to 2. So first of all, that is twice as wide, but what if this area is really tiny here and this area is really tiny here? It wouldn't double the area by stretching from -2 to 2. So this one is actually also not possible to determine. Part F, the antiderivative from -1 to 4 of f of x plus h of x dx. Okay, well, I can separate the f of x and h of x bit here, so -1 to 4 of f of x dx plus the antiderivative from -1 to 4 of h of x dx. Now I know the antiderivative from -1 to 4 of f of x dx is -2. I don't know this one. -1 to 4 of h of x dx. So this is also not possible to determine. Now try problem number 1. This big old paragraph up here says, please don't use your calculator. Number 1, suppose that f and g are continuous functions and we're given this information here. So the integral from 1 to 2 of f of x dx equals -4. Integral from 1 to 5 of f is 6. The integral from 1 to 5 of g is 8. Use the rules to find each integral. Okay, so the antiderivative from 2 to 2 of g of x. So here's my g of x function. And here's 2. If I want to find the antiderivative from 2 to 2, that rectangle has width 0, so that is definitely an integral of 0, zero space in there. Part B, the antiderivative from 5 to 1 of g of x dx. Well, let's see. G, I know 1 to 5, so that's going to be the opposite of the integral from 1 to 5 of g of x dx. So that's going to be the opposite of 8, so -8. Part C, the integral from 1 to 2 of 3 f of x dx. Well, then I can take that coefficient and put that outside of the integral because it would belong to each of my rectangles, so I can kind of factor it outside of this sum. And then the integral from 1 to 2 of f of x dx is -4, so 3 times -4 is -12. Part D, the integral from 2 to 5 of f of x dx. I know 1 to 2. And I know 1 to 5. I need to know 2 to 5. So you know what I'm going to do? I'm going to take, so I know 1 to 5. And I know 1 to 2. So I'm going to take out 1 to 2 from 1 to 5. So I'm going to take the integral from 1 to 5 of f of x dx, and I'm going to subtract the integral from 1 to 2 of f of x dx, and that's going to leave me with the area between 2 and 5, the signed area between 2 and 5. Okay, so that would be 6 minus negative 4, so that's 10. Part E, the integral from 1 to 5 of f of x minus g of x dx. So I'm going to split that subtraction. I can do that. Addition and subtraction can be split, or the integral can be split over addition and subtraction. So the integral from 1 to 5 of f of x dx minus the integral from 1 to 5 of g of x dx. So let's see, from 1 to 5 of f of x is 6. 1 to 5 of g of x is 8. 6 minus 8 then would be a total signed area of negative 2. So there's 2 more units below the x-axis of this f minus g integral from 1 to 5. And finally, part F. This is a several stepper here. The integral from 1 to 5 of 4f of x minus g of x dx. So I'm going to separate the f and g parts first. So let's see, that would be the integral from 1 to 5 of 4 f of x dx, not gx, minus the integral from 1 to 5 of g of x dx. Alright, now I can factor out the 4 because that's a coefficient, so 4 times the integral from 1 to 5 of f of x dx minus, and then that can stay. And now I know these values. The integral from 1 to 5 of f is 6. The integral from 1 to 5 of g is 8, so 24, minus 8 is going to be 16.